So I think we can start if the speaker is ready.
Yeah,
Well, let me simply say that it is always a big pleasure to attend the seminars on webinars on non-associative algebras. So I'm trying to be here every Monday, even if the schedule is not very compatible always with my own schedule. But anyway. It's a big pleasure to see young people presenting their new achievements. And on this occasion, we have another young researcher who is actually from my own university, and actually I'm one of his supervisors. And the speaker this afternoon is Gerardo Martín Escolano. I hope he has a long, promising future ahead. So, and today he is speaking on some results obtained for his PhD, and some of them are already published on preservers on Jordan Banach algebra. So, Gerardo, you can begin
oh,
whenever you wish.
thank you, Anton. Well, first, thank you to the also to the organizers for letting me give this talk. And okay, and this talk have different parts. I will talk about different results we obtain in the ambient of preserver problems, and at the end, I will talk about and the Mackey-Gleason band grade problem, which is a recent result we obtained. And let's start first making a brief review about Jordan algebras. And well, we know that a Jordan algebra is a real or a complex Banach space equipped with a bilinear mapping, where this will is the notation for the Jordan product that satisfies the following properties. This property related with the norm, and these two properties. This one is like the Jordan product is always commutative, and the second one, which is called the Jordan identity, related with the algebra of the space. A natural example of a Jordan Banach algebra is when we consider a Hilbert space and we take the space of bounded linear operators. If we define the natural Jordan product this way, we obtain that B of H has the structure of a Jordan Banach algebra. And there are different classes of Jordan Banach algebras. For example, the GB algebras, which are those Jordan Banach algebras satisfying this identity related with the square of any element and also this inequality. In case this space is kept with an involution and satisfies that the involution of the element is the norm of the involution and the element is the same, and also this identity, we have a GB star algebra. And these two classes of Jordan algebras are related due to a result by Wright in the 1977, where the self-adjoint elements of a GB algebra, which are the elements which that satisfy that the involution of the element is equal to, to the same element, and well, each GB algebra corresponds to the self-adjoint part of a unique GB star algebra. Now, if we wonder why we should study Jordan structures, I want to I want to talk about this quote of Arsenal and Schultz that says, which is related with the quantum mechanics, because and when we consider C-star algebras or for Neumann algebras, they are used to talk up for the algebraic model of quantum mechanics, and the observables are represented by the self-adjoint part or by the self-adjoint elements of this space. But and the self-adjoint part of such an algebra is not closer and the given associative product, but is closer to the Jordan product, and that's why it's important to use the Jordan algebras rather than the associative algebras to study the quantum mechanics. Now, in particular, in this talk, we will focus on the two classes of Jordan algebras, which are the GB algebras and the GBW star algebras, which are those GB star algebras or respectively GB algebras, which are also dual Banach spaces. And These algebras are unital, and also they have a relation between each other in the same way as GB algebras and GB star algebras, due to a result by Edwards in the 1980s that says like every self-adjoint part of the algebra is a GB algebra. Now, why focusing on GB star algebras? Also, I want to remark this quote by Edwards that says when we want to study symmetries of different physical systems, it's useful to study the complexification of GB algebras and GBW algebras, and this is the case that we will find in the along the talk. So now, after this brief review of which is the setting we are going to work, let me start with this first section, where we consider the Lie-Trotter formula in Jordan Banach algebras and application to the study of spectral-valued multiplicative functions. Now, in current research in functional analysis, and in particular in preserver problems, are interested on considering when the traditional conditions of linearity can be removed from the classical results, at the cost of assuming the preservation of any algebraic or geometric property. This is the case of the famous Gleason-Kahane-Chelasco theorem. The Gleason-Kahane-Chelasco theorem states that when we have an associative complex Banach algebra, then a non-zero linear functional phi is multiplicative if and only if it is spectral-valued. Then a natural problem on preserver problem arises, which is the following one. If we now consider f a multiplicative functional from a unital complex Banach algebra, if we suppose that each x of the algebra, for each x of the algebra, f of x lies in the spectrum, we wonder if f is going to be a multiplicative linear functional on A. And Mauche considered this problem in the 1996, and he established the following result. When under the previous conditions, when we consider a map F not necessarily continuous or linear, there exists a unique multiplicative linear function of C on A that agrees with F on the connected component of the identity in the group of all invertible elements of A, what is called the principal component. And this result in particular is optimal in the sense that F doesn't need to be in general linear. As we see in the following example, if we consider A to be the continuous maps in the interval 0, 1, and we define this following functional phi of F equal to 0 if F is 0 at some point, of F of 0 if not, and we additionally assume that phi of the multiplication of the two functions is equal to phi of F product phi of G, and that phi of F is spectral valued, then defining these two functions, f of t equal to t minus 1 and g of t equal to 1, we obtain that, well, the phi of g plus f is equal to 0, but this is different from phi of g plus phi of g. And so, about this problem, we have obtained obtained positive answers for commutative unital C-star algebras by Touré and Brits, for von Neumann algebras by Touré, Schulz, and Brits, and for unital C-star algebras by Brits, Mabrouk, and Touré. So the principal aim of this study, which is a joint research with a joint work with Antonio Peralta and Armando Villena, which has been already published, is to study the problem 1.1 in the case of unital complex in Jordan Banach algebras. But before stating what is going to be the problem in this case, let me make two brief remarks. The first one is related with the principal component. In the case of an associative Banach complex Banach algebra, we know that the principal component of this space can be written in the following way, as finite products of finite elements of the exponentials of elements in the algebra. Now, if we try to obtain a similar formulation for the principal component in the case of a unital Jordan Banach algebra, we know that usually the product of invertible elements are not in general invertible in Jordan algebras. So an expression similar to the previous one, changing the associative product for the Jordan product, is hopeless. But we know, due to a result by loss, that the principal component in the case of a unital Jordan Banach algebra can be written in terms of the U operators of exponentials of elements, where the U operators are defined in the following way in respect to the Jordan product. And the second remark I want to say is related with the maps. When we consider unital Banach algebras in the associative case, and we consider a unital but not necessarily linear mapping, then delta is a multiplicative or anti-multiplicative and satisfies this property related with the U operators. Now, when A and B are unital Jordan Banach algebras, and we consider delta a unital but not necessarily linear mapping, we know that when this property is satisfied, then delta preserves the squares, which is equal to preserve the Jordan product. This makes us consider a new but natural hypothesis in order to consider this problem in the setting of Jordan Banach algebras, and is the following one. The problem we will try to solve is when we consider a functional, not necessarily linear, from a Jordan algebra, satisfying that f of the U operator of x evaluated in y is equal to the U operator of f of x evaluated on f of y. When it satisfies this property and f of x is Jordan spectral-valued, we wonder if we will find a linear map that is equal to the map f in the principal component of this Jordan algebra. And also, if we assume that f is continuous, we wonder if f is going to be a Jordan multiplicative linear functional on A. And we will see how we have gained a complete positive answer to this problem, and our approach is slightly different from the arguments applied in the setting of C-star algebras, and they perhaps are slightly simpler. And the first part is about, we will talk about the Lie-Trotter formula. And the Lie-Trotter formula, when we are working on associative complex Banach algebras, is a result that says when we have two any arbitrary elements, then the limit of this product of the exponentials is equal to the exponential of a plus b. So, as when we were wondering, wondering about a new expression for the principal component, now we wonder what will be a nice expression, a nice formulation for the Lie-Trotter formula in this context of Jordan Banach algebras. Perhaps we can consider changing the associative product by the Jordan product. Also, we can consider this expression in terms of the U operator, or even more general, we can consider this expression in terms of the U operators of two elements, which are defined in the following way. With this definition, now we see that the U sub A operators are just a particular case of these ones. Now, and when we consider associative unital Banach algebras, this Lie-Trotter formula that we propose can be deduced from the classical one just by applying the following identity. However, we cannot apply the same argument when we consider an arbitrary unital Jordan Banach algebra, since the theorem we applied to prove the previous result is purely algebraic. We are applying mainly the Kirchhoff-Cohn theorem. For this case of a general Jordan Banach algebra, we will employ the holomorphic vector-valued functions. And a quick definition of what is a holomorphic vector-valued function is we first have a Banach space, a function f from an empty set of the complex numbers. Then we say f is holomorphic if these limits exist. and for all lambda sub 0 in this open set. And also, we know that if we have an holomorphic a map F is holomorphic if and only if it's weakly holomorphic. This is like for every map in the dual space of X, the function phi composition of F. This is not the Jordan product, this is the normal composition, and this map is holomorphic. Then the main result related with the Lie-Trotter formula is the following one. When we consider a unital complex Jordan Banach algebra and we take a map F from the disk from the disk centered in 0 and of radius r in C, when this is an holomorphic map such that f of 0 is equal to the identity, and we suppose additionally that we have two sequences lambda sub n, a sequence in the disk, which limit is 0, and another sequence such that satisfies that the limit of the product of these two sequences is equal to lambda, then for a sufficiently large n, this expression is well defined, and we have the following identity, that the limit of this map of this expression is equal to the exponential of lambda multiplied by the derivative of the map f in 0. This theorem, note that is also valid when A is associative, an associative unital complex Banach algebra. With this theorem that give us many identities in these two settings, we can obtain the Lie-Trotter formulae we proposed at the beginning, and that I sum in this corollary. Well, now when we have a unital complex Jordan Banach algebra, the following identities they hold. Now, in the next part, we will try to focus on the Gleason-Kahane-Chelasco theory in Jordan Banach algebras, because in the results by Mauche, he tried to apply this in Gleason-Kahane-Chelasco and the Kowalski-Minkowski theorem in order to obtain his theorem. So when we start studying this problem, we try to obtain first a Jordan version of these two results, the Gleason-Kahane-Chelasco that I stated before, and the Kowalski-Minkowski theorem that says when we have a complex Banach algebra and we have a map delta, not necessarily linear, a functional satisfying that 0 goes to 0, and that the difference of the two evaluations, they belong to the spectrum of I minus b, then we have that delta is a linear and multiplicative functional. So, and we first obtain a Jordan version for the Gleason-Kahane-Chelasco, which is the following one. When we consider a complex Jordan Banach algebra, a non-zero linear functional, then the following statements are equivalent. Phi is Jordan spectral-valued, phi is Jordan multiplicative, or phi is unital or admits a unital extension to the unitization of A and maps invertible elements in A to non-zero complex numbers. The proof, the most difficult part, is proving that A plus C is obtained using the Gleason-Kahane-Chelasco theorem for Banach algebras. In the case of the the Kowalski-Minkowski theorem for Jordan Banach algebras, we notice that the original proof by Kowalski-Minkowski works in this case. So now, and in order to obtain a similar result as Mauche obtained, and we will, in order to obtain the same thing, our arguments do not require any applications of the Kowalski-Minkowski theorem, as in the Mauche's work, but we will use a Jordan version of a weaker algebraic lemma due to this author. And this is the following one, that when we have a complex Jordan Banach algebra and we have phi and R linear spectral valued functional, then phi is linear. Using this lemma, and we obtain this main result of this part, which is the following. When we have a unital complex with Jordan Banach algebra and f is a non-necessary linear functional satisfying the property we discussed before, and that is Jordan spectral valued, then we exist a unique continuous Jordan multiplicative linear functional psi such that f is equal to psi of x in this for every x in the connected component or set of all invertible elements containing the unit element. This is the principal component. Finally, another remark about this result is when we consider a map F satisfying the previous hypothesis, we obtain that F is one homogeneous also. And finally, let's focus on the problem in the problem of continuous spectral valued multiplicative maps. Now, if you remember in the problem 1.1, in the case of associative algebras, we also wonder that if F is continuous, when we add continuity to the problem, if we obtain that F is going to be linear also. Adding continuity to this associative problem has been solved by Briggs, Mabrouk, Schultz, and Touré for commutative unital C-star algebras, for unital C-star algebras, and for von Neumann algebras. The tool they applied is the following one, that for each continuous multiplicative spectral valued functional f from a unital C-star algebra A into C, and each element x of A, this function that takes lambda to f evaluated on x minus lambda. This map is analytic on the unbounded component of C minus the spectrum of x. So, and to obtain a similar result in this setting of GB star algebras in this case, we establish an extension of the use quoted tool by showing that under more general hypothesis, the commented function is in fact affine. Now, applying this result and the Jordan version of the Maucher theorem that we saw in the previous subsection, we can turn our attention to this problem 1.2 in the case of unital GB-star algebras. So the result we obtain in this case is what we expected, that when we have a unital GB-star algebra and we have a functional f, not necessarily linear, satisfying that f is continuous, this identity, and that is a Jordan spectral valued, then f is going to be a linear Jordan multiplicative functional on A. And now we can rediscover the main result for unital C-star algebras, combining the previous theorem with a result by Chelasco, and we obtain the commented theorem by Brice, Mabrouk, and Touré for unital C-star algebras. And the following section, we will focus on preserved problems of commutativity. We know that when we are in quantum mechanics, the observables are represented in terms of self-adjoint operators of Hilbert space. Now, and when we take two observables and we want to measure them simultaneously, they can be measured simultaneously if the self-adjoint operators that represent the observables, they are commutative. That's probably why the preserved problems of commutative elements have been widely studied. The first result we find for associative algebras is the following one by Bresar and Myers in 1993, where they says the following: when we take two von Neumann algebras with no central summands of type I1 or I2, and we have theta, an additive map which preserves commutativity in both directions, then there exists a central invertible element, a Jordan isomorphism, and an additive map such that the formulation of phi is written in the following way. Furthermore, if theta is a symmetric mapping, it satisfies this property with respect to the involution, then J is a Jordan star isomorphism. And if we find now a similar result for Jordan algebras, we have, first of all, when we try to consider this now we know that the Jordan product is commutative. So when we wonder when two observables in these Jordan structures, when they are going to be compatible, we explain that in terms of the commutativity of the operator commutativity, or what is the same in terms of the associator. The associator is defined on the following way for any three elements in a GB star algebra. So in the setting of Jordan algebras, we have the following result by Bresar, Eremita, and Villena of 2003 that says the following. We have M and J non-quadratic unital centrally closed prime not degenerate Jordan algebras over a field K of characteristic different from 2, 3, and 5, then for every bijective linear mapping phi such that satisfies this property, which is equal to say that the elements phi of the square of A and phi of A, they operator commute, then there exists a non-zero alpha, a Jordan isomorphism, and a linear mapping such that the map phi can be written in the following way. Now, the principal aim of this study is a joint work with Antonio Peralta and Armando Villena, a study that has been already published, is to extend the quoted result by Bresar, Eremita, and Villena to linear bijections, preserving operator commutativity in both directions between GB star algebras admitting no central summands of type 1, 2, or 1, 1, a la Bresar-Myers. So, and the technical core of this study are related with the elementary operators. When we consider a GB star algebra and we write this way P of J for the Banach algebra of all bounded linear operators on J, we will write this in this form for the subalgebra of B of G generated by the multiplication operators M sub A with A running in J. The elements of this set is what we call elementary operators in J. Furthermore, when A is running in the self-adjoint elements of the GB star algebra, this set will be denoted by this subalgebra will be denoted this in the following way, and furthermore, it satisfies in this relation respect to the involution of the element. So the main result we obtain here are the following two. The first one is that when we consider a GB star algebra with no direct summands of type I1 or I2, then we can find a self-adjoint element in the algebra and three elementary operators such that satisfies this identity. This is that when we consider this operator and we consider the power of any power of this operator of this element U, then we obtain this delta. And furthermore, in the case we consider a GB star algebra with no direct summands of type I1, then what we obtain, we can find this element, this self-adjoint element, but we now obtain only two elementary operators satisfying the property. Now, and also the other element or the other technique we applied in this study were the factor representations. So also we have the following result relating this in elementary operators with in Jordan star homomorphisms, and the result says the following, that when we consider a factor, well, in this case, this result is more general. When we consider a Jordan star homomorphism between GB star algebras such that the image of is weak star dense, then for each elementary operator, we obtain a unique elementary operator, in this case in M, satisfying this property. Now, once we have these results, we start studying and first of all, associating linear maps on GB star algebras, associating traces on GB star algebras, and applications, finally, to preservers of operator commutativity. The first part related with the associated linear maps, our aim is to prove that when we have a GB star algebra with no direct summands of type I1, then if we consider a linear mapping such that preserves the operator commute with the image, or equivalently that the associator of x and t of x is equal to 0 for all x in J, if we can write t in the following way, where lambda is a central element and mu is a linear mapping from J to the center of J. In order to obtain this result, due to the structure theory of GB-star algebras, we developed different techniques for the following cases. The first one we obtained was when J is a GB-star algebra without type I1 summands, and the second one is for purely exceptional GB-star algebras. In both cases, the idea is to apply the previous elementary operators in order to obtain an explicit expression of the element lambda and the mapping mu on every factor representation. The result we obtain then is the one I stated before, that when we have a GB-star algebra admitting no direct summands of type I1 and T is a linear mapping such that the associator of every element x and the image T of x is equal to 0, this is the operator commute, then T can be uniquely written in the following form when lambda is a center element of G and mu is a map from J to the center of J. This map is linear. Now, we extend our study to associating traces on GB-star algebras. As in the previous part, and our aim now is to consider when we have a GB-star algebra with no direct summands of type I1, and we have B, a bilinear symmetric mapping such that the image of every trace, for every element x, the trace of this map is equal to 0, well, the associator is 0 for all x, and we want to prove if B can be written in the following way, where as before lambda is a central element, mu is a linear map from the algebra to the center of the algebra, and nu is a bilinear symmetric mapping. And as before, due to the structure of the GB-star algebra, we developed different techniques for the next cases. The first one, when G is a GBW star algebra without type I1 or I2 summands. The next one is when J is a purely exceptional GB star algebra, and the last one when J is a type I2 algebra. And as in the previous case, the idea here is to apply again the elementary operators to obtain explicit expressions of the element lambda and the mappings mu and nu on every factor representation of the algebra. And as a sum, we obtain the next result that says the following, that when we consider a GB-star algebra without direct summands of type I1, and B is a symmetric bilinear mapping such that satisfies this property, this is x and the trace of B, the operator commute for every element x of J, then B can be written in the following form, where, as I said before, lambda is a central element of J, mu is a linear mapping from J to the center of the algebra, and nu is a bilinear and symmetric mapping from the algebra to the center of the algebra. Furthermore, if J is a GBW star algebra of type I2, then we can say that the element lambda is going to be always 0. Finally, all these results related with linear maps and traces we will apply in order to obtain results for preservers of operator commutativity. So the aim in this case is to consider two GB-star algebras M and J admitting no direct summands of type I1 or I2, and take a phi a linear bijection preserving operator commutativity in both directions. This is like when x and y, they operator commute in M, then this only happens if and only if the images operator commute in J. So in that case, we want to prove if phi can be written in these terms. Well, Z sub 0 is a central invertible element in J. G, in this case, is a Jordan isomorphism, and beta is a linear mapping. In the proof, or a brief sketch of the proof, and a brief sketch of the proofs will be the following one. And the idea is to consider this bilinear mapping B and given in terms of phi and the inverse of phi. And since we know phi preserves operator commutativity in both directions, then we know that the inverse is going to preserve this operator commutativity too. Then this mapping, this defined in this way, is symmetric and it satisfies these properties. It satisfies in the preservation of operator commutativity. Then we obtain this this relation with the associator of the bilinear map, which is just the same hypothesis we considered when we were studying in traces of bilinear maps in the previous section. So the idea is to apply the previous results in order to the previous results on associating traces. Finally, which is more difficult, but and the rest of the proof is related with proving the invertibility of the element set sub zero, that J is a Jordan isomorphism, and finally the uniqueness of the formulation we proposed. After that, we obtain our decided result, which is the one I said, that when we have two GP star algebras and maintaining no direct summas of type 1 or type 2, and we suppose phi is a linear projection preserving operator commutativity in both directions, then phi can be uniquely written in the following form, where z at 0 is invertible, is a central element invertible, J is a Jordan isomorphism, and beta is a linear mapping. Also, we will think that as a corollary, we can obtain this same result when we are considering the self-adjoint parts of M and J, but so we can state the following result, which is not trivial and related with the self-adjoint parts of the algebras. And the result says the following: when we are considering GB star algebras and without direct summas of type 1 or type 2, and now we consider the same linear rejection, but between the self-adjoint parts of the algebra, such that this map preserves operator commutativity in both directions respect to the self-adjoint parts of the algebras, then we can say that phi can be uniquely written in the following form. But in this case, Z sub 0 is a central element in the self-adjoint part of J, and J in this case is a Jordan isomorphism between the self-adjoint parts of the algebras, and finally P is a linear mapping between the self-adjoint part of M to the center of the self-adjoint part of J. And now, the next section is in order to study surjective preservers of operator commutativity. Why? Because it is natural to ask whether it is possible to replace the bijectivity of commutativity preserving mappings by some mild conditions, like is surjectivity. So the present section is devoted to study the surjective linear mappings preserving operator commutativity between GB star algebras and admitting no central summands of type I1 or I2. This question is even new in the setting of von Neumann algebras, and the results of this section and also the ones related with von Neumann algebras is a forthcoming work with Antonio Peralta and Armando Villena. And before stating the main results of this study, I want to make a brief remark because it's one of the techniques we applied, and it's just a general result concerning to classical theory of linear spaces and linear mappings between them. And it's the following: we have a pair of linear spaces, X and Y, and a map phi, a surjective linear mapping between them, then there exists a unique linear mapping psi from Y to X such that the composition is equal to this element, where the juxtaposition refers to the classical composition of functions, and this the identity is well, and this element stands for the identity mapping on Y. Now, as we did before in the case of bijective maps, we start studying associating linear maps on GBW star algebras. And the result we obtain in this case is the following one. When we have a GB star algebra admitting other exobands of type I1 or type I2, and X is a complex linear space, we see here it has not any structure such that is a linear space, and we have two linear mappings, T and phi. Then if we suppose that phi is surjected and it satisfies this property, this is that the operator T and the element F, well, the maps T and phi, they operator commute respect to the same element, then T can be uniquely written in the following form, where lambda is going to be a central element in J, and mu is a linear mapping from the linear space to the center of J. And equivalently, for associating traces on GB star algebras, we obtain the following result. When we have a GBW star algebra without summands of type 1 or type I2, and X is a linear space complex, considering the two maps, this symmetric bilinear map from the complex linear space to the GB star algebra, and this surjected map from X to J. And if we suppose additionally that B, the trace of B and the map phi, they operator commute for the same element in X, then B admits a unique representation, which is the following one, and it's very similar to the ones we obtained in the case of bijective, in the previous case, and it's the following one, that P of X can be written in this form, where lambda is a central element of J, mu is a linear mapping, and V is a symmetric bilinear mapping. Finally, we can use these two results for linear mappings and for traces in order to obtain the desired result for maps preserving operator commutativity when they are surjective. So the result we obtain is the following one. Let's take M and J a pair of GBW star algebras with no central summands of type I1 or I2, and let phi be a surjective linear mapping preserving operator commutativity. In this case, we don't need to preserve operator commutativity in both directions. We only are asking to preserve commutativity in one of them. This is if we have two elements in M preserving operator commutativity, then we need that phi preserves operator commutativity of the images. Then there exists an invertible element and V, an homomorphism J, and a linear mapping theta, such that phi has this unique representation. Furthermore, if phi is a star symmetric mapping, then this element is self-adjoint, J is a Jordan star isomorphism, and theta is a star symmetric mapping too. And a sketch of this proof, in order to remark which difference we have in this case, is that we saw in the bijective case, we defined a map in terms of phi and the inverse of phi, but in this case we cannot do that since we don't know it exists. So in this case, we only define this bilinear mapping B in the following way, and in this case, this map by definition is symmetric and also satisfies the following identity with respect to the associator. So now we can apply the previous result in the case of associating traces. And that will be a brief sketch of the proof. And as a corollary, since a von Neumann algebra is a type of GB star algebra, then we obtain this result for any pair of von Neumann algebras. This is when we have M and J, any pair of von Neumann algebras with no central summands of type I1 or IV2, and phi is a surjective linear mapping preserving commutativity. When now we see we are using the Lie brackets, not the associator, then there exists an invertible element in the center of J, a Jordan homomorphism, and a linear mapping such that phi admits this unique representation. Furthermore, also, if phi is a star symmetric mapping, then the element double V is self-adjoint, J is a Jordan star homomorphism, and theta is a star symmetric mapping too. Now, the last part of this talk will be focused on the famous Mackey-Gleason transcribed problem for vector-valued measures on projection in a GB star algebra. So, let me first start making the following definition and about what is a countably additive positive measure. And a countably additive positive measure on the lattice of all closed subspaces of a complex Hilbert space H is a mapping mu which assigns to each closed subspace K sub I on H a non-negative real number, and it satisfies this identity. Now, and this identity for every countable collection of mutually orthogonal subspaces of H. Now, Mackey in 1957 he proposed the following problem. He wanted to determine all the measures on the closed subspaces of a Hilbert space. And the solution was made by Gleason. He posted it in the 1958, and he stated in the famous Gleason theorem that says the following: when we have a separable Hilbert space H of dimension at least 3, this is important, and every measure on the closed subspace it can be written in the following form, where T is a positive semi-defined self-adjoint operator, and P sub K denotes the original projection on the closed subspace in K. Now, the Mackey-Gleason problem, Gleason after this posed the problem of determining all the measures on the projections in von Neumann factors. So, and why we, in this case, he was considering a Hilbert space of dimension at least 3. A counterexample due to Caddison shows that the conclusion doesn't hold in case of the dimension of the Hilbert space is equal to 2. For example, and the example is the following. The counterexample is the following one. We consider this Hilbert space of 2 times 2 matrices and taking valuation C, and we only have to consider the following, and we consider the following two projections. P sub 1 is this matrix, and P sub 2 is this matrix. So now, by defining the map mu from the lattice of this space into the interval 0, 1, where mu of the identity is equal to 1, mu of 0 is equal to 0, mu of P is equal to 1.5 to 1/2, and for every P that is which is not P1 or P2, and we consider now that the image of P1 is 0 and the image of P2 is equal to 1. So now if we try to prove that mu can be written in these terms as the trace of this projection and of positive semifinite self-adjoint operator, and we will get that this is impossible in this case. Now, and the Mackey-Gleason Banach problem. So now when we are considering, let me first start defining what is an X-valued measure, a vector-valued measure. When we have a lattice of projection, for example, in this case, in the one we are going to study, a GBW star algebra, and X is a Banach space, then bounded finitely additive X-valued measure on the lattice of projection is a mapping satisfying these two properties, that the map is additive respect the finite sums of mutually orthogonal projections in the lattice, and also that is bounded. This is like the supremum of the norms of the evaluation of each projection on mu is finite. Then the Mackey-Gleason Banach problem is asks whether a bounded finitely additive x-valued measure on the lattice of projection of a von Neumann algebra, or more generally, as in this case, a GBW star algebra with no type I2 direct summands, is the restriction of a bounded linear operator from J to X. Now, positive solutions have been obtained for this problem. First of all, between the 82 and the 1982 and 1984, and Christensen and Jedon obtained positive answers, a positive answer in the case of positive measures on the lattice of projection of an arbitrary von Neumann algebra with no type I2 direct summands. In the 1985, and they find a positive answer when they are considering countably additive positive measures on the lattice of projections of GBW star algebras, and this was made by Vance and Wright. Between the 92 and the 94, Vance and Wright also found a solution, but when they are considered bounded vector-valued finitely additive measures on the lattice of projection of von Neumann algebras with no type I2 summands, and also due to the contributions of other experts such as Arnes, Kumson, Maeda, etc. And finally, in a preprint, and in a joint work with Antonio Peralta and Armando Villena, we obtained this result for bounded vector-valued finitely additive measures on the lattice of projection of any GBW star algebra with no type I2 summands. Here we see in a timeline of how much of how positive answers to the Mackey-Gleason problem were obtained. And as a result of this new, as a consequence of this new result for GBW star algebras, and you know that in the case of associative algebras, the Mackey-Gleason problem has multiple applications. So, and we expect that, and with this new result, we obtain many new consequences, and we can obtain new results for GBW star algebras. For example, one of the applications of this new result is the piecewise Jordan homomorphisms of unitaries. First of all, let me define what is a piecewise map in the associative setting. Now, if we consider a set endowed with a binary operation, then noted this way, we say a set is piecewise closed with respect to this product when we make the product of any two elements, then they commute. They are commutative. Now, and let's now consider two sets with a binary operation, this one, and let A and B be piecewise closed subsets of these two sets. Then a map is called piecewise homomorphism if it satisfies this property whenever A and B they commute. Now, in a forthcoming work with Jan Halter, Antonio Peralta, and Armando Villena, our principal aim is to study or to explore the Jordan piecewise isomorphisms between the sets of unitaries of GBW star algebras without direct summands of type I2. Now, in this, for the previous results or the results we applied in order to make this study was the previous one for maps, bijective maps preserving operator commutativity. And also, we will use a result for well, we apply this result. And but in this case, as we are going to work on Jordan algebras, we will need to define what is to be a piecewise homomorphism in this setting. Did I run out of time, Antonio?
1 minute or 2 minutes, a couple of minutes.
Okay, no, just okay. Now, when we are considering Jordan algebra and when we will say that if piecewise closed in case that every two elements we have that the operator commute. So we will say a map between closed sets of two Jordan algebras is this map is going to be piecewise homomorphism is in case that this identity holds when any two elements the operator commute. So now if we try to, well, knowing this, well, these are the definition of what is a unitary on a GB star algebra, which are only invertible. It's well, an element in a Jordan algebra is a unitary in case it is invertible and it inverse coincides with the involution. And well, this is the definition on one parameter groups. So using this result due to Maria Cueta Avellaneda and Antonio Peralta related with the and with these sets of unitaries for GBW star algebras, that in the case of GBW star algebra, we say it has this expression, we finally obtain the following theorems. Well, we have the theorems and saying that in case we have a bijection between unitary groups and phi and phi minus 1, they are continuous, then they are equivalent that phi is a Jordan piecewise homomorphism, that there exists a map between the self-adjoint parts of the Jordan algebras and satisfying this identity, and also that they comport properly respect to the U operator. Also, we obtain the following result in terms of expressing any map between, well, when we have any pair of GBW star algebras, if we consider this map between the unitary set of non-trivial Jordan, well, if we obtain a non-trivial Jordan piecewise isomorphism, this map can be written in the following way. And finally, also that when we have factors and this a continuous projection between the unitary sets of these algebras, then phi is a piecewise Jordan isomorphism if and only if there is a Jordan isomorphism theta such that one of the following conditions holds. And that's all. These are the references, and thank you very much.
Okay, thank you, Gerardo. I know the tremendous effort to try to transmit all the problems in which you have been working. It's very difficult. I hope the audience could get an idea of how difficult the Jordan setting is with respect to the associative one, and how many answers are still being unexplored, even in this 21st century. So I should ask anyone in the audience would like to pose a question to Gerardo, or to say a comment, or to add something to the results. Now is your time. No questions, I think. I see no questions, no comments for the moment. Well, anyway, I think it's very difficult to digest so many new results and so many new directions. Anyway, the setting of Jordan algebras is passionate, I think. Geometrically speaking, they are even more natural objects to study than von Neumann algebras. And in some of the cases, even the results for Neumann algebras are completely new. And I hope you can defend your PhD, and you can have a good welcome in the Jordan community, and you can continue keep on doing this good research. So thank you so much to Gerardo, and I hope to see all of you next Monday. So thanks a lot to all of you for coming. Bye bye.
Bye.